Okay, so it is time that we discuss about the SuperCollider server, the audio server. Of course, this is maybe the reason while you're working with SuperCollider. So actually, before we had to do along the tour, but I think it is worthwhile because now we have the possibility of having a control interface, a very complex control interface for audio synthesis processes. So even if until now we know nothing about how to generate sounds, but at least once we add this small, well, it's not a small part, but once we add this part, we will be able to adopt all the techniques that we saw before to this in order to control this task. So in order to speak about the SuperCollider in terms of sound processing, we need to remember a basic aspect of SuperCollider. You will remember that we said that while we in the SuperCollider application there are many components. One is the editor, the one we have in the background of this video. The other is the interpreter that until now we have used and that is active, and we know that the interpreter is connected through a network to a server, SuperCollider server, which is a synthesis, audio synthesis engine capable of generating high quality audio in a very efficient way. Now, just to sum up, the idea is that the Sklang program, the one including the interpreter that we are using, is working like a client for the server. This means that the server and the Sklang program are connected through a virtual network, and the Sklang, so the program, the component including the interpreter, can work as a client for the server. This means that if we need sound, we need to ask for this kind of service to the server. Now, in fact, in the few cases that we until now we generated sound, we've been in need of having the server working. So the point is, when there is sound, then there is the server working. There is no other possibility in SuperCollider. As you will see, there are some tricks that in some sense might hide the presence of the server. In some sense, what we did before by using the construct, we decided to this kind of construct look like there's no server at all, but at the end, if there is sound, this means that the server is at work. Now, how do we boot the server? In this way. Just consider what is going on here. Now, we knew from our first meeting that this is an instruction that boots the server. But let's consider this. This is a formal language, so there is nothing related to properly to black magic. So this should mean something. Can we analyze this? Well, surely. What is S? S is an environment variable. It can be nothing other thing. It's a single low case letter. So this means that S is an environment variable, just like the ones we used, like A, F, or whatever. And here we are sending a message to S, meaning, hey, S, boot yourself. So what is S? Well, there is nothing mysterious about this S, but the point is that when we open the interpreter, all the single letters are available as environment variables, but by default S is already bound to the server, so that we can immediately control the server from the language. So, in fact, if you ask to S, hey, what are you? Localhost. Localhost may be a sort of strange name, but this means the server. Can you use S? Yes, you can, but it's better that you do not do it, because it is very useful to have S already bound to the server, so that you can control the server immediately, like this. And in fact, here the server is starting. You can see some useful information. Some of this information have already been discussed. Surely you can see this information, which is interesting. It says sample rate 48,000, meaning that we have 48,000 samples as for each second. So this is the default sample rate. The default sample rate, it means that for each second, 48,000 samples are captured and used to represent the sound. This means that 1 second of sound is represented by 48,000 values. Internally, SuperCollider works with 32 bits. So we have, for each of these samples, there is a 32-bit number, floating point number representing the value. So, can you change the sample rate? Can you change the sound card you're using? Yes, you can, by means of a specific class, the name of which is server option. I'm not diving into this. You can look at this by yourself, but you can, of course, change the sample rate to whatever value you prefer, and there is no maximum in SuperCollider apart from the fact that you need to have an harder compliant sound card, or better, a sample rate compliant sound card, and you need to have CPU on your computer. So now we have booted the server. This means that the server here becomes green, and we are ready to generate sound. And the point is, how do we generate sound in SuperCollider? That's a completely new chapter. So the basic idea is that, as we know, is that we are working in a client-server architecture. This means that the server should be completely autonomous from clients, and clients should not incorporate anything crucial for the operation of the server. So the server actually acts as a sort of engine provided with some specific components, and all these components and the whole server as a unity can be controlled externally by means of OSC messages. So there are some components available, and all these components presents an interface to the external. This interface is a set of OSC, Open Sound Control messages, and in order to control the server, we have to send to the server the opportune OSC messages. You may ask yourself, but here we send the message to the server because we asked the server to boot, but I cannot see any OSC message. That's a tricky point and a very interesting one, because the point is that the language supercollider includes a lot of classes which are related, which represents objects of the server, and they encapsulate the communication with the server. So, as we will see, substantially, we will have not to deal with this OSC interface, but we will be able to keep on working in our usual way by controlling objects in the SuperCollider language in the way we discussed before. So the point is that there is a layer, required layer, speaking OSC, but the point is that on top of this layer, the SuperCollider language builds a set of syntactic elements that are handling for us all this communication. This makes things much easier, and if you think about this, it is exactly what happens here, because here we should have sent to the server, and the server should be reached by means of a network address, and we should send to this network address a command. Now you cannot see any network address, and you cannot see any specific OSC command. Everything is handled by what? Well, in this case, by the server class. The server class encapsulates a set of methods capable of controlling the server. The same things happen for the various objects that are used by the server itself. So, what is on the server? Well, we can take a look to this. Figure. Well, let me check, because I was looking for maybe a different figure. No, this one directly. It is interesting. So this is a sort of ontology of the server. What does it mean? It means that this diagram tries to show all the available elements on the server. So the server is made up of all these objects. This is the server. You might think of the server as a sort of farm, and this farm is made up of machineries, and these machines are made up of elements, and all these machines are able to communicate among them. That's the main situation. So, the very basic element we have to take into account is the so-called synthdef and synth. Let's write this down. Synthdef and synth. Now, if we take into account those names, well, it's clear that synth is an abbreviation for synthesizers, so a device capable of generating sound. So you might simply think of a synthesizer as an electronic music instrument. This instrument can be very complex and complicated, but this instrument can be quite simple. Just think about a electronic audio hardware. You can have complex machine like a synthesizer with a keyboards and various knobs and so on, but you can also have a single oscillator built into a machine. You just switch it on or off with fixed frequency. So, the point is that something capable of generating sound in real time is a synth. The question is, how do we create a synth? And here comes into play synthdef. The synthdef is simply a definition of a synth. So, suppose you want to create a synth. The first thing that you have to create is a project for this synth. And the project of this synth is its synthdef. That means its synth definition. So it's just like you want to create an electronic device, and by soldering various components on your boards, diodes and whatever, before doing this, you should know what to do, and typically you should have a project for a schema for in order to lead your work in creating the actual synth. Now the schema is typically on paper and it doesn't make sound. This is obvious, okay? The schema doesn't make sound. It's a piece of paper, but from that piece of paper you will be able to solder on your board all the required components and have an instrument that, when switched on and receiving currents, will generate sound. That's the point. That's the point between synthdef and synth. So, you cannot create a synth if before you have not written down, defined its project, that is, its synthdef. So a synthdef is something in some sense abstract. It's a sort of project that we have to provide to the server. It works like a blueprint, and once there is a synthdef, then we can ask the server to create a synth from this synthdef. It's just like that before having an instrument, we go to the server that acts as a manufacturer, provide the manufacturer a project, and then once the manufacturer is given the project, we can say, hey, manufacturer, please make me a synth of that type, model DX7. So the first thing we have to do is to create a synthdef, and we know that synthdef will not sound, but will provide a blueprint to create a synth. The synth will sound in real time, so when you play, you work with synths. If you're playing live or generating sound, this means that there should be synths at work. There is no other way in SuperCollider. So if you look at this as this picture, you can see that here there is no, if you consider this like a farm, a working farm, at working hour, this is a synth, you see, and the synthdef is the project for this machine. Where do you store the project for this machine? Well, probably on the farm's archive. So we have to assume that somewhere in this farm there should be a sort of archive capable of containing the project that have been used to create those synths. As you can see, this is not all what we have in our server. There are other components. I'm naming them like buffer, agents, groups, and buses. So, in order to make a synthdef, we have to provide the server, in order to make a synth, we need to provide the server a synthdef. How does this process work? Well, actually, you can see that I wrote these, and this is a name of a class in SuperCollider, because it starts with a capital letter. If it starts with a capital letter, it's a class. In fact, we are provided on the language side of a class synthdef that will be used to create a new synthdef. Now, you will typically never see the new. We know that it means it simply means that the new can be omitted, and which are the parameters, the arguments that we are required to provide in order to make a synthdef. The first is a name. What is the name? Well, it's the name of the project. Think about the situation. You go to the server as a manufacturer and say, please make me a synth. You need to provide a name. Synth model Yamaha DX7. So you need a name. And this name must be associated to the synthdef. And there can only be one name for a certain project. So there cannot be two names or one name used for more projects. So single name for a single project. That makes sense. So how do we provide names? Well, you can use, if you want, strings, but a typical construction use symbols. What is a symbol? Well, actually, it's a little bit complicated, but you can think of symbols in SuperCollider, which are prepended by this slash, in terms of names, specific names. A string is a sequence of characters, while a symbol is a name, like your own name. So, this is a symbol, okay? So, like the name of your project, and it is the first element that we have to provide in order to create a synthdef. The second is a function, a specific function, which is called Eugen graph function. Function for the definition of a graph of Eugens. So function. Okay, it's a function. In fact, we have curly braces. And this function is used to represent a graph that is a structure like a tree, substantially. Thus, a structure connecting what? Connecting basic units capable of generating signals, audio signals. Eugens. Eugens stand for unit generator. It is a classic of computer music. A unit generator is a unit that implements a certain algorithms for the generation or for the processing of a certain signal. So if you look here, you can see that each synth is made up of a connection, a specific graph, a connection of Eugens. So Eugens is just like the basic units implementing certain audio algorithms for reading, writing, generating, processing signals. So the Eugens are the main responsible for the generation of signals, and they can be connected together. This connection is typically called patching. You patch a Eugen into another. More on this later. So actually we're trying to describe something like this. That is, this should be a diagram that we want to provide. One might say, why don't we provide a graphical schema? Well, actually because we're using a language. So we're writing down, we have to write down this kind of organization. And before filling up this function, let's try to have the largest picture. So the idea is that here we are creating a synthdef. And what to do with the synthdefs? Well, a synthdef on the language side, on the client, means nothing. In the sense that you cannot do anything with a synthdef because a synthdef works on the server. So typically what happens is that you will never find something like this. So the association of a synthdef instance to a variable, because on the language you will not work on a synthdef. The only thing you do with synthdef is creating them and sending them. This means, well, think about the fact that here there should be a sort of, there should be a new. So what happened here is that here on the tail we will have a new instance of a synthdef. This instance of a synthdef will receive the add message, meaning synthdef go to the server. At this point what happened is that we have this project is compiled, and once it is compiled in a format that we are not interested into, is compiled and sent through a network connection, local of course, on your machine, but it's a network connection, is sent to the server. So this is an empty instrument, just like you buy an instrument which is an empty case. So can I buy that instrument? Yes, it's really cheap, and they give you just the case. This is our test instrument, but if you look at this number here that could be different from 109 I have here, now let's evaluate these. And what happened is that this number increases because it was, in my case, 109, now it's 110. The definition, this number is telling you how many synthdefs are available on your server. When you start the server, probably some synthdefs will be automatically loaded for you because of the history of your installation, because of your version. This is not relevant for us here. But the point is that once we did this, we are adding a synthdef to the server. For how long does it remain on the server? Until the server is switched on. When we quit, we stop the server, then the synthdef will be flushed away. So now we have a new synthdef. And what can we do with this synthdef? Well, even if it does absolutely nothing because it is an empty case, we have sent the server a project detailing how to create an instrument made up of an empty case. Can we create a real instrument from this project, a bit bizarre project? Yes, we can, in this way. Here we make a synth, so we have a class which is synth, representing on the language the notion of synth on the server. So again, we do not have to send OSC messages asking the server to create a synth. We do this in our normal way, standard way. So we create a new synth, and as you can see here, the first argument we have to pass in order to create a new synth is the name of the synth. Because, of course, you want a synth. Which kind? Which type of synth? Sure, we want test. Now, look here at this second number. This number here is 0. There are no active synths. S stands for synths. Now we're creating this, and something is appearing here, and you can see that now we have one active synth on the server. These numbers represent the average, the peak and the average CPU used by the server. So you have a certain number, a certain idea of how much CPU you are consuming. And this number represents the number of active agents. Now this is 0, and it remained 0 even if when we created the synth. Why? Because our instrument is an empty case. There's nothing working inside. There are no agents actually, but everything is working. So that's the way: create a synth and send it to the server. Then you can create an instrument from it. That's the way it works. How do we destroy a synth? Well, we do not have the need to destroy a synthdef. We just leave the synthdef. That's not an issue. They are temporary. When we switch off the server, everything goes away. No problem. But the synths are active processes. They can be consuming CPU. How do we destroy these synths? Well, we will see that it is possible to use variables to manage synths, but if we forget to assign the synth to a certain variables, how do we send message to this synth? Again, the panic button comes handy, so control dot or apple dot or whatever, and we kill everything. In fact, if you see here, there is 0 for the synth name. Now, that's interesting to be able to create instruments that are void. Maybe they can be used for a sort of illegal market when in which we are trying to sell completely empty instruments, but that's not what we are interested into at the moment. So we need to put some gear inside this instrument, and so we need to describe their internals of a certain synth, our test case. So going back to the diagram, the point is that actually we have created tests like a synthdef and a synth, and we have just provided an empty case. Point is, we need to add some of these things and to connect them. So we need to put inside Eugens. And in order to have something working, at least, typically, we need a couple of Eugens. Something generating signal and something sending this signal to your sound card. To be more precise, to send it so that we can intercept the operating system and whatever. But the point is that we need to be connected. We need to send this signal to the sound card. That's our the basic point. So let's consider the most basic unit generator we can use. Well, it's not the most basic, but the most common. Generator for sinusoidal signals. Sinusoidal signals are very important, very typical, very historically important. They are used as components of many instruments, and we need a way to generate sinusoidal signals. How can we do this? Well, we have a specialized Eugen doing this. Guess what? It's called SynOSC, Synosc or Synos. I will pronounce it as Synosc for, well, because I'm used to, I'm sorry. So Synosc. And Synosc is an oscillator that generates sinusoidal sound. Now, Synosc, as you can see here, is represented by a class, because we are on the language. So we need to find ways to express, to represent these aspects of the server. If we look at this image, Synosc is a Eugen, one of these things. Now, what happened is that we need to ask Synosc to generate sound, or better, to generate a signal. So let's keep on this idea on audio signals, and we can do this in this way. Let's consider this linguistically. This is a message we are sending to a class, and in this case it means that when a class representing a Eugen receives an AR message, it generates an audio signal. So outside here we have an audio signal. What is an audio signal? It's a computation working in real time of values representing sound. So synosc.r will return a sequence of values representing a sinusoidal signal. Now you have some arguments for this AR, meaning audio rate method, and those are some arguments that we can easily imagine. So we have the frequency of our signal, how many times the sinusoidal cycle is repeated in 1 second. Typically, by default, it's 440, meaning an A. Then we have the phase. Do we want to start from 0 or do we want to start from another point? Then we have mul and add. Mul is a multiplier, add is something to be added to the signal. Mul and add are so common that substantially all the UGENs include a mul and add parameter. What does this mean? It means that a sinusoidal signal, generically a signal in SuperCollider, is generated in the range, in a normalized range, going from -1 to +1, this representing the maximum and the minimum values in your format, that is 32 bits. So we are working from -1 up to +1, so it's a bipolar representation with the average, the zero, meaning no displacement, no, as the how can I say, intermediate line. Mul is a multiplier to be applied to this signal. So if by default it goes from -1 to +1, then we multiply this for 0.5 and it will go between -0.5 and +0.5. So it's a way to scale the amplitude of the signal. Add is a value that is added, a value that will be added to the same signal. So it's a sort of offset. By adding a constant value, we offset the signal. As you can see, all the UGENs, they have a basic. They have default values. It's very important they have default values, so you avoid curious things with zeros or nil values in the audio. So now we are generating a sinusoidal signal. Default parameter, it will be an A, 440. Let's evaluate this again. What happens? That we are sending to the server a new test. It's always called test, so we are overwriting the previous one. There can be only one synth with that name. So we are overwriting. Everything seems to work fine. It's always 110 to definition because it's the same name. Now let's create the synth. Okay, now we have one synth. I was expecting something different. Let me see. Right, we have one synth. We still have 0 UGENs. But okay, let's do not consider this. What we have to consider is that we are not hearing anything, because actually we are computing the sinusoidal signal, but it stays on the server. The point is that from the server we have to take this signal and we have to pipe it to the sound card. So the problem is piping this signal to the sound card, and here enter buses. You see bus here and you see bus there and there. The point is that buses are like pipes to which we connect signals. So there can be external and internal buses, meaning that some pipes are used to communicate from outside to the outside of the server, like in bus and out bus here, while other buses can be used, if you want, for internal communication inside the server, that is among various synths. So the point is that the minimum requirement is that once we have created a signal, we have to pipe it to one of these out buses so that it can reach the sound card and be played back. So let's see how we can do this. Well, first of all, we can do something like this. We assign the signal, which is a sequence of numbers to be generated in real time, to a variable sign. And the point is that we have another UGEN which is called out, and it's a meaningful name. And out requires, again, as all UGents, an R message, meaning it has to generate an audio file. In this case, rather than a generation, it's a piping, but still meaning it still means that it has to deal with signals. And so we pipe on the bus 0, later on this, what sine. Now what happened is that we are creating sinusoidal sound, and we are piping this signal on the bus 0. It will mean the left channel. Let's see what's going on. I'm switching immediately this off just to prove it was working. It was a sinusoidal signal. So, well, but let me see this. Yeah, just look here. Look here, you get 2 UGents, 1 synth. Probably without having out, we were not able to see the UGents at work. Now we have seen that we have 2 UGents, Synosk and out, at work in one synth. So what happens is that we have created an audio signal. So we have a project, and we can create as many audio signals, many synths as we want. Let's try first of all to connect SuperCollider to recording, and jack input client, right, and here we should be able to, well, thing we can do immediately is that we can have a second synthdef. Let's call this test 2, and let's change the frequency. So now we have test, and now we have now. So we have created 2 synths. The point is that we need to control a little bit better the amplitude of the signals, but I want to introduce some aspects before. So the idea is that we can create how many synths as we want, provided that we have enough CPU and in general computational resources. So the point is that once you have the project synthdef, you create on the fly, and as we will see, you will interact with synths. Synths are your main interface to generate sound. There's nothing else. When there is sound on SuperCollider, there is a synth, at least one synth at work. So can we add some control here? Of course we can change parameters. Like here, we can have test, Synosk, let's use mul. We can use arguments. Suppose we want to keep our frequency at 440 and just change the multiplier, we can use keywords. Normally, as we do while writing, mul, and mul, let's use mul as, let's do this. And here we say, so we have this damned sinusoid at a quite lower amplitude. So what happened here is that we are piping on the bus 0 this sine in this instrument, which is 440 Hertz, and while this other instrument is a slight variation on the one before, so it's just 110, and will be piped on bus 1. How do we know what these numbers mean? Well, actually the convention is that the outputs of your sound cards are represented by progressive indexes or indices as you want, so progressive numbers. So left is 0 and right is 1 if you are on stereo, but if you have 4 channel 0, 1, 2 and 3 will be used to control the four outputs. And if you have 8 channels, 0 up to 7. And what happens if you are in stereo and you use the index 2, 0, 1, 2? Well, actually, that will become an internal bus. So you will write inside SuperCollider. So actually, what we are doing here is that we are piping into left and right two different instruments. So our instruments are connected, one to left and the other to right. These are just projects. Then we create one. That's a little bit better. And the second one. We can also... Okay. Fine. But there is something that is not satisfying for us. First of all, every time we have to destroy all the synths, because the only way we have to kill the sound is to kill the synths by using the panic button. Can we do something better? Of course we can. We can use variables. I'm using single letters for sake of easiness. And at this point, we can also create them on the fly, both. So we have two synths assigned to X and Y, and we can do something like this: is run false. We are pressing the pause button, so it still exists, but it's not working. It's not generating sound. And of course, you can do something like this: X run true. False and true are Boolean reserved words. Again, it is. And suppose you're bored by Y. Can you destroy Y? Yes, just in this way. Now, what happens is that Y synth, which is test2, its model is test2, is destroyed, freed. So we can do the same thing for X. No more synths. So now X, you might say that it represents a synth on the language, but at the end, on the server, there is nothing more. So if you want to create again the synth, you can in this way. Okay, fine for control, but if you look at these two synthdefs, this is pretty boring, because substantially we have duplicated the code in order to add control. Can we do something better than this? Of course, we know that a function might include arguments, and typically what happens in a function is that arguments are used for what? For input. Now, in Eugen graph functions, the idea is that the arguments represent the inputs, the control inputs of your synth once it is created. So, as an example, just think about Eugen's functions. Sorry, if you think about functions, what happens is that this name is used as a proxy that can be used later in computation. Now, this fr will be used here, while this out will be used here. Good practice says that we need to provide default values, otherwise situation can get complicated. So now we do not need any more test, because this can do all what we need. We only have to change the value of fr and of out. So let's see what happens here. Here we have our synth test. Default is 440 and it's on the left. Fine. How can we make another synth matching the values of 110 on the left? Well, we can do this. Now it's exactly the same, but there are two synths, and we can control in this way by sending the set message to Y. So synth Y, set your argument fr, you see this is a symbol, with the value, but we also want to control what happens with out, and so we want to send it to the other channel. And we have exactly the situation we had before. So we're now what happened is that let's kill everything using the panic button. Now if we consider our synthdef, the project of our simple instrument is a sort of case enveloping an sinusoidal oscillator that from outside can be controlled in frequency and can be controlled in terms of the bus that to which it will pipe the sound. It has a fixed amplitude 0.1. It's a linear the description of the amplitude. And what happened here is that we can think of this substantially in this way. So if we draw the schema, we see that what happened is that the sequence of values generated in real times with this parameter by Synosc are patched into the Eugen out on a bus which is no more fixed because we have developed it. So now it can receive a value from outside, like frequency here, and this sequence is patched into channels array. So think about these boxes as internal modules that can be wired together. So what we did here was to wire the output of synOsc to one of the input arguments of out. So we did a first case of patching. Now, can we do something better than this? Well, first of all, even if with a sinusoidal generator like this, things can become a little bit more interesting if we know how to control this simple instrument. So we see that we can control this from keyboards. That's something like a live coding. So just by writing, we create and control sound. But let's take into account graphical user interfaces. So let's do something like this. Window, we create a window and then we create a knob like the one we already created. We're making some exercise. This is wrong, and should have dimension. Just copy this dimension and paste it. So classic mega knob. And now the point is that k action could be, let's try to bind everything. K action could be we know a function arg me, which is the knob. And why? Because here what we want to do is to bind the rotation of the knob to the control of the frequency. So me value lin 0 1 going from let's say something like 1000 to well, maybe it's a little bit too much, 100 to 1000. This is a frac variable, and we want to do something like x set. So this small program requires, we can clean up this, and now this small program should work. So let's see what happened here. This is our synth. Now we have this small button here. Right, this small GUI control an aspect of a synthdef. You can have much more complicated synthdef, but the point is always the same. So we're doing some binding. Let's free this. No more synth. Now, actually, if we move the knob, probably there will be some issues. Right, in fact, it said, okay, failure in the server, because I cannot find the synth you're asking for. So you're asking for a synth, but that synth has been destroyed. Okay, so what happened here? So this is a small program, if you want. This program is made up of 3 parts. That's important. On top, you're asking to boot the server. Well, this can be interesting in the program because it means you're using sound. You can also use SuperCollider not to generate sound. In this case, of course, we're generating sound. Then we have a block like this. Why have I put these brackets here, these parentheses? Well, the point is that to create a synthdef and to create a synth is an asynchronous process. First, you have to tell the server that you are creating the synthdef, and only when the synthdef is created, you can create a synth. Otherwise, you get an error. Now, synthdef compilation is ultra fast, but still must be done in 2 steps. So the first thing is to send the synthdef, and then this block can be used all together. And here it is. And we can add this in order to destroy everything. We don't need it, but we can do something like now with this line we are freeing the synth on the server and we're closing the window, so we can do everything from code, but we're using graphical user interfaces. So this is a program, and the way you should write programs when you deal with audio. Well, there can be much more complex approaches, but the point is that first things related to compilation of synthdefs, and then blocks related, in this case 1 block, creating the whole setup of synths and their control. Fine, can we do something a little bit more exciting? Well, this wasn't bad because we had GUI and connected it to synthesis. Can we connect processes to time processes to synthesis? Well, let's suppose we have something like this. We have a synth, so we know we can control the frequency. Fine. R as a routine doing what? Well, this is what we will do. You see that sometimes I wrote a sort of skeleton, frame, and then fill it up in order to have the idea clearer. Now, what does this routine? What does this routine do? Well, actually, infinite time do, not raw, but do what? Well, the idea could be simple like this: x set fr frequency, like what? Like rand is an instruction. You can use it written in this way, but also in these other ways. Like it will gives you back a number between 100 and 1000. So we generate a random number between 100 and 1000 hertz. And we set the synth to this value, and then we wait something like a fifth of a second. So here we have our Do you like old style video games? If we stop the routing, the last value keeps standing. Now, can we do something more interesting again? Well, surely. First of all, we can also say that x set out. We can make jump our sound swap between channels. Now, this is quite discrete. So one, so left or right, nothing in the middle. We can do something in the middle, but not now. So this is a case of choosing a discrete value like this. Not wait. Why? Choose. So here we're picking up 0 or 1. Right, as usual, semicolon. Now, can we see this jumping in some way? Well, luckily, yes. If you do something like this, so you send to the server, you can send to the server some messages in order to show what's going on, like scope. And here you see, now by default I have 10 tracks because they are the outputs of my cards, but I can see only 2 tracks. And you will clearly see that we are swapping, so this is what is happening on the server. And of course you can have it larger if you want. Maybe you're curious about the frequency. And here we have our frequency. We're scoping one of the buses, so as it's swapping we only see what's going on in bus 0. You can see what's happening in bus 1. Also, of course, the frequency analysis works on one bus, and it is always a sinusoidal signal, so you will always have this kind of representation. So there is a built-in frequency analyzer and oscilloscope. Okay, so this is interesting also because we can think about control. So a sinusoidal oscillator, all these eugens that require a frequency must be controlled by passing hertz. That's a logical attitude because we're working with the physical technological aspect. But when you're controlling when you are controlling this instrument from a musical general perspective, our ear does not work in this way. So let's consider 20,000 hertz. Seems like many. Point is that what is going on between 100 and 200 is the same that is going on between 10,000 and 20,000 because it's just one octave. So thinking in terms of octaves and pitches, even if you're not interested in harmony, is a good way to control things, because what is linear for frequency is not linear for hearing, and working with pitches is a good way to have a good linear representation for you in relation to pitches. So as an example here, we do not want to choose frequency, I would like to choose between pitches. How can we do? Well, actually, let's consider this. We could bring in our approaches before 0, 3. Let's take a minor scale just to give you an idea. So this is a minor scale, and we want to choose among these pitches, and we can add a bass like middle C. Fine. Now the point is that we are not in hertz here, but we are in pitches. How do we convert hertz to pitches? Well, it's pretty easy, because if you do you can use messages to be sent to numbers like this one, MIDI to CPS cycle per second is like hertz, and in fact you get back to 161 and something. Of course, as you can imagine, The same works with CPS to MIDI. So our case is MIDI CPS. So now we are selecting pitches between pitches among the natural minor scale of C, that is C minor natural, and we're converting this in pitches, in hertz. Of course there are glitches because we are swapping randomly. The same kind of attitude is useful if you're working with amplitude. Now, amplitude in signal is always described linearly. So you're going from -1 to +1. And if we're scaling these, we're scaling linearly. The point is that linear amplitude has really nothing to do with perceived volume. So a good way to deal with this is to use decibel, because even if decibel is a technical scale, it's a good representation of, actually a much better representation than linear amplitude of what happens in terms of volume. So, is there a way to which we can control amplitude? Well, sure, like this. We call this as amp and say that amp is 0, 1, and here we have amp. So now we have added another control. Notes that these arguments, they represent the input of your synth. It's just like your input now, your synth comes out with one knob or a possible connection, one more possible connection. Now it has 3 possible connections. So we have a new synthdef, and the other point is that we'd like to set also x set amp, and we'd like to do a random choose between well, probably this is not necessary. So here we are choosing a possible value in the range -30 up to 0. We know that in dB, or in one of the possible representation in decibel, 0 is the maximum possible. That's the way SuperCollider thinks, while -infinite is the minimum, and typically -96, if you are in 16-bit, is the real, is the 0. So -30 is a low volume, while 0 is the maximum. So we're choosing a value here and converting this value, which is in dB, in linear amplitude, and passing this value to our synth. So every 0.2 seconds, we are creating new parameters and controlling the synth. Same mistake I keep on doing since 15 years. You see, we have a variation in volume. There are a lot of clicks because we're swapping randomly between signals. Okay, let's stop this. So the point is, a synthdef is the project that we are using, and a synthdef like this provides 3 possible control input for the generation of signal. We need at least a couple of fusions, one generating sound, the other piping out this sound to the sound card. And here we have Synosc. We can modify this if we want. There are many generators, and many of these periodic waveform generators substantially have the same syntax. As an example, pulse, it generates a square waveform. So let's check this. It sounds different, obviously. and you can have like this one, which is so I think it has, you can check the help file to see if the parameters are the same. Substantially they have, you see, of course they are fixed waveform generators, so substantially you have frequency, multiplier, and mul and add, and you can have something related to in case of a square waveform, a duty cycle, or in other cases you can have phase, but substantially basic control is the same. Let's try with so. And yes, first sounds different, of course, because it has a different harmonic internal spectrum. So an interesting point is how many synths can we have? As I told you, once you have one synth, well, you can have many synthdefs, and you can have many synths from a single synthdef. The number of synths is just up to your computational possibilities. So it can keeps on growing until you have a CPU and RAM that can be used to, how can I say, feed those processes. So the basic idea in SuperCollider is that you first boot the server. Once the server is on, it can receive synthdefs, and once you have synthdefs, you can create synths. How do you create synths? By interconnecting UGENs. So let's take a look again. Here you can see that we have patched a Synosk UGEN, like it was in this place, to an out UGEN. And of course there are still other things that we have to take into account. We have seen buses, at least out buses, so like pipes where we can throw out sound. We can use buses to receive sound in input, and also to stream sound from one synth to the other. Then there are buffer, a very interesting object. It's buffer, and we will see in the next videos. So okay, I think that's enough to try to understand synthdef for now, and work with synthdef, and just using this kind of situation, just using a UGen generator and out, one can explore the various generators. Where do we want can we see these UGens? Well, if you go to the help file, you see classes UGens, and here you have all the UGens you need, and they are grouped by type in some sense. So as an example, we can look at generators. These are all generators, like deterministic generators, single value, stochastic generator, chaotic generator, and so on. So there are a lot of things like Synosk. You see, these are deterministic generator, and we will see in the next video some of these UGen. The last thing I'd like to add for now is that we saw an example of patching, because we saw that yes, the signal coming from sine, let's stick back to, was patched into out. But what happens to the other parameters? Can we control this? Well, surely we can. So as an example, var vibr So what I'm doing here is that I'm generating a control signal, meaning that this signal is not used to be directly fed out to the sound card, but it is used to modify the FR parameter. So the FR parameter, let's consider defaults, it's 440. Now we will add something going from -5 to +5. So in the minimum situation it will be 435, at its maximum it will be 445. So it will oscillate around 440, and it will oscillate with a frequency of, well, with a frequency of 5 Hz, so 5 times each second. So let's see, we can hear something with default values. You see there is a vibration in the frequency. So now we have patched the output of Synosc R, and we have patched it to the input of the sine block. So we have a double, we have 3 Eugens here, 2 Synosc connected through the frequency argument, and an out. Now what can be finally introduced here is that if we take a look here, we see that we are using the R message. It will output a signal with at sample rate. It means that each sample, that is by default 48,000 times each second, a new value will be calculated. Fine. This means that for the Nyquist theorem we can represent up to 24,000 Hertz. Now, what is interesting is that here we're using a very, very low frequency. This is a sub-audio frequency. Now, the Nyquist theorem tells us that in order to represent this variation, we would just need 10 Hz, a sample rate of 10 Hz, and now we're using 48. This means that for most of the new values, these values will be substantially very similar to the previous one. Do we need to update every sample, also the output of this Eugen? Or maybe it's a waste of computation? So, in SuperCollider, like in many other computer system for audio synthesis, we have the possibility of using different rates, and in particular one is the audio rate. Computation is updated at every sample, and a control rate in which computation is updated only in relation to a block size. So every, let's say, 10 samples, every 1000 sample. So this means that this signal will have a lower resolution, but that's not the point, because it changes in a very slow way. So even if at a lower resolution, we still get all the information we need. So as you will see here, even if we update at control rate the control signal, it sounds exactly the same. Now, computation on our fast machine doesn't cost as it costed some years ago. So even if you're doing this, well, yes, you're using a little bit more of computation, but it doesn't change in a meaningful way. But that's a good practice to think that in this case it is really useless to have audio rate updating of this signal, because this signal changes in a very slow way. So audio rate and control rate, everything going to your loudspeakers, that is to your sound card, must be, of course, audio rate. And in fact, these should be matched by these. So this, in fact, it's at audio rate, it's the output of Synosc R, and it is received by out. So next time we will dig more into this synthdef, that means also in synth construction.